code. And then based on that, you will then open the Arduino IDE and change the settings to have the sketchbook folder pointed to the top directory of the source code you just downloaded. You also want to change the default settings on Arduino. By default, it will rename files that have the old PDE extension to the INO extension. We don't really want to do that because it will just mess up the code. So for now, uncheck that box if it's checked in your configuration. Now, a little tip. Arduino IDE needs to be restarted between changes. It doesn't like having its preference changed. It doesn't like the files underneath it changing, and it doesn't find libraries if they're changed while it's open. So generally speaking, when you make a change with the Arduino IDE, if something isn't working, it's probably because you forgot to restart it. So after you make a change, always restart the Arduino IDE. Then set the board to the Arduino Mega 2560 or ADK option. Set the serial port to the correct serial port, click Verify, click Upload, and there you have it. You've just compiled your Arduino code for the first time. Again, as I mentioned before, this presentation will be available so you can follow it as a quick start guide that will get you up and running quickly. Another method to compile the code, which some of our developers prefer, is to use the Eclipse open source integrated development environment. Eclipse is cross-platform. It's a Java-based development environment that runs on pretty much everything that runs Java. So first of all, you'll need to download the C++ version of Eclipse. There's a link there for downloading that. And then follow the initial setup instructions in the ArduPilot Mega wiki to get all your editor preferences correctly set. Once you've done that, there's some tips here on how to change your settings to get it working. So for example, change the build command to make, or make with the build root, which is the folder of your choice for where you want the executable stored. Change the build directory to the workspace and subdirectory of ArduPlane or ArduCopter, depending on what you want to build. And then change the build target from all to APM2 or software in the loop or one of the other targets. So by changing these three parameters in Eclipse, you can then very easily with Control-B or Command-B build the project, compile it, and have it running. Now, our Windows information is a bit sparse, but basically the three tools, equivalent tools that can be used on Windows very easily. Arduino 101 for your compiling of the code. For editing the code, Notepad++ or Eclipse or something else will work too. And for using Git, the most popular interface is called Tortoise Git. And Tortoise has some good instructions on the wiki for how to use Tortoise to do most of the functions that we need for this particular project. All right. Next, Linux. You can, of course, do the development on Linux. You would need the Arduino IDE for Linux, as well as specific AVR GCC and AVR libc libraries. So to install those, very simply on Ubuntu, you can install the packages Arduino GCC AVR and AVR libc. On Fedora, you can install the RPMs for AVR GCC, AVR GCC C++, and AVR libc. Those would be enough for getting your libraries up and running. By the way, any developers want to jump in, just jump right in. I've got the lines unmuted. Be happy to have you add anything at any point. Now, the other little tool you need on Linux, and we'll see the same thing on Mac, is for uploading flashing to the APM. If you don't want to use the IDE, you can also use AVR-Dude. And AVR-Dude is a flashing program that will transfer the hex onto the board. All right. And on the Mac, which is the platform I use for development, you will need the basic build tools. So things like Make and things like that come as part of the Xcode application. And that's the Apple development environment. You'll also need the Arduino IDE and either a graphical user interface or a command line Git client. So I use SourceTree, which is a free graphical user interface from Atlassian. It's quite nice. I can show it to you here. And this is what SourceTree looks like. On my screen, there we go. So that's what SourceTree looks like. It shows you, various branches, various commits and revisions, et cetera, et cetera. All right, I can see from the chat that some people are having audio problems. Can people on the phone hear me?
Yes.
Yes.
Okay, someone can hear me. Great.
Yes.
All right, so apparently if you are having problems with the audio, you may need to quit your browser and reopen it. And I would recommend, if you're having difficulty with the online audio, to try using a hard telephone line or a cell phone to call in. You might find it easier. All right, moving on. Now, one of the things that is a bit of a challenge when developing on Linux or the Mac is the issue of a ground control system. So with Windows, of course, we have the fantastic and excellent Mission Planner, which is very nicely integrated with ArduPilot Mega. However, on Mac, it's a bit tricky. So on Mac on Linux, you can run the Mission Planner in a virtual machine. A lot of people do that using, say, Parallels or VMware Fusion, and of course in Linux equivalent virtualization software. You can also use Mono, and Mono is a disease, but also it is an emulator for .NET. So Mono can be downloaded for both Mac and Linux, and it provides a runtime environment for running .NET applications. And you can run Mission Planner under .NET to a certain extent. So it works. Some things work better than others, but you can get a lot to work. Two more alternatives for the ground control system. Ground Control is a Qt application that is cross-platform, works on Mac and Linux. It provides a rather sophisticated ground control system. And finally, my favorite, the completely underutilized and totally deserving of more publicity, Mav Proxy, which started out as a proxy for Mavlink, but is now a very sophisticated Python-based cross-platform command line interface for ground control systems, and has some sophisticated modules with graphical capabilities, including a moving HTML map. And finally, for building the code, a lot of the developers prefer to use command line for many of the functions. So I personally do all of the compiling without the Arduino IDE. I use Eclipse for my development, and I also use command line in order to build the software. It's very easy. You can use the make files that are in the software. And to do those, you might want to define some environmental variables. The first one is build root. And what build root does is it defines where the hexadecimal or executable, the libraries and the various compiler artifacts will be stored during compilation. The makefile build is used for general development, but it's also the only option if you want to build software in the loop or the auto test configuration for the software. And we'll talk a bit more about software in the loop and hardware in the loop in a second. Yes, now the other nice advantage, of course, as Mike suggests, is if you have the Arduino IDE but you're using the command line, you don't need to restart the Arduino IDE every time you change something. So The command line allows you to compile everything right off the file system. Within the make files, if you look carefully, you'll notice that it uses a rather complicated make file, which is in libraries AP Common Arduino.mk. That make file actually uses some rather complex auto-discovery and search-based discovery process to find where your Arduino IDE is. So that helps a lot with cross-platform compatibility. If that doesn't work, however, you can point it directly to where your IDE is by setting the Arduino environmental variable. The default target, if you just type make, is for APM1. Make APM2 will do the APM2 version, and make upload will push that hex and flash it onto your board. You have to define the serial port, which is in the config.mk file in the root directory. All right, so basically compiling the code can be as simple as 2 lines. As you can see here, cd ArduCopter, make APM2, and that will make the APM2 version of ArduCopter. Or cd ArduCopter, make CTL, and that will make the software in the loop version of that. All right, let me just pause there before we move on to the next section, and I'd like to see if people have any pressing questions on development environments on Windows, Linux, and Mac. And of course, I'll invite the other developers to jump in and help me out answering those questions. So let's see if we have any questions right now. And you will have to unmute. You'll have to unmute your microphone in order to speak.
What does the make CTL do again?
Oh, CTL is the software in the loop configuration. Basically, instead of running, say, ArduCopter on the APM2 board, you can run ArduCopter on your computer, on your laptop, on Windows, Mac, or Linux in a simulated environment. And then you can use that to drive a simulator, to test the software with a ground control system, essentially do all of the flying you would do without any hardware at all, just all emulated in software. It's extremely useful for developing code.
How about ATML IDE 6.0?
I have no idea. Probably yes. Anyone want to take that one? Any of the devs? Can you use the ATML IDE 6.0?
That's Visual
We'll take
Studio.
that offline. And the AVR Studio, yes. I believe you can compile the code with AVR Studio, and I believe there are some instructions in the wiki, and I can get a more direct answer to that question.
Thank you.
All right, what compiler should be used to compile the mission planner? I believe that's visualstudio.net, but I am not sure. I have never managed to compile the mission planner because I don't have a Windows machine. I don't know if Michael is online. Or if anybody else can answer that question.
Yeah, it's, can you hear me?
Yes, Adam, go ahead.
Yeah, it's visualstudio.net. What you need to do to get it to compile properly is to copy. What I've done is I've copied all of the DLLs from the release bin folder, which you'll find if you're familiar with .NET, you'll find it in there. Just copy all those DLLs into the debug bin folder, and then it should compile properly, and you can make changes in there.
Okay, and Andreas, this is Robert Lefebvre. I just wanted to make a comment because I missed the slide when you were talking about the Windows. It was me that added those Windows programs, and I just wanted to point out I think the Windows users are probably going to be a lot of entry-level users, which is what I am, or was. I found Notepad++ to be really easy to use and powerful enough to be able to just kind of surf the code and find things. I just jumped right into it and was able to figure out how to work really well. So that should be something that any new people looking into this stuff on Windows, you should definitely download Notepad++. It's free, works really well.
Don't ever come downstairs.
The only other point to know about that using Notepad++ is that it won't compile and upload at all. So I basically do any surfing or editing in Notepad, and then I go into Arduino to do the compile and upload. So it's a bit of a pain that way, but it's the best I've found so far. I tried Visual Studio, and I found it just way too powerful and complex. It's very powerful, but for a beginner user who doesn't use it a lot, it's a little bit... it's a bit much.
And I should quickly note that Visual Micro for compiling the Arduino solution will no longer work as of, I believe, 2.6 version of our firmware because the Visual Micro plugin is not compatible with the new version of the Arduino IDE.
All right, very good information there. Okay, I would definitely second the idea that Eclipse is not for beginners. If you are unfamiliar with Eclipse, don't bother. It will just be a huge pain, and this is not the project where you try to learn Eclipse. So that will just confuse you. I would recommend using a simple editor and the Arduino IDE, as Robert suggested. And Eclipse really is, if you are already familiar with Eclipse and you really like it as an environment, then that would be a great place to develop because you'll be comfortable with the IDE. Okay, moving on. So for configurations, now the main code has a lot of different configuration. Obviously, you have different vehicles that can be compiled. So ArduPlane, ArduCopter, APM Rover, ArduBoat, et cetera, et cetera. Within each of those, you have different sub-configurations. So for example, in ArduPlane, you might have the standard, VTail, Flying Wing, Elevon configuration, et cetera. In ArduCopter, you have a traditional trad heli, as we call it, or a traditional helicopter, main rotor and tail rotor, quad, hexa, and octa multi-rotors, and various configurations of those. In APM Rover, there's only one configuration at the moment, but who knows? Already some people are discussing having a second configuration in Rover for tread vehicles that have differential steering, so that might be interesting. Now, separately from the vehicle configurations, you also have build configurations, and really this is about the target of your configuration. So a build configuration might be APM1 or APM2 for the two boards we have. In the past, we also had options for Mavlink 0.9, Mavlink 1.0. And there are various other little options like that, like if you want to compile a special version with no GPS, or if you want to compile a special version for some other weird configuration. Then the other two modes that are really interesting are hardware in the loop and software in the loop. Just to briefly explain what those mean again, Hardware in the loop, you're running the code on the APM, but the APM is actually, instead of using its own sensors to see where it is in the world, it takes information from a simulator on the computer about where it is in the world. And that means that it can execute all of the code as if it's flying, even though the APM is sitting right there on your desk, not moving at all. The computer will simulate accelerometers and gyros and barometers and GPS entries so that the board thinks it's flying. And that way you can test exactly how the code will behave on hardware. Software in the loop is the same thing without the board. Everything's simulated in software. There's a part of the code that will simulate the physics, so accelerometers, gyros, barometers, etc. And then there's a part of the code that basically runs what would be running on the board, say ArduCopter, but runs it on Linux or Mac or whatever your desktop is. All right, and finally, hash-define customization. So many of the options within the code are parameterized so that they can be turned on or turned off using preprocessor definitions in C++. So using hash-defined, you can change the value of a parameter or enable or disable a big chunk of the code. And we're going to see exactly where that goes in just a second and how you define that. So this takes us to the guided tour of the code. And this is where I'm going to need help from more developers. And we're going to get started in just 1 second. Let me just switch screens. All right, so everybody should be able to see the latest version of the code. What you see here on my screen is Eclipse, and what I'm looking at here is the most recent version of the code. So I have used Git to download the latest version of the code. As you can see, I believe it's this one. And now that I've downloaded this code, I'm opening it in Eclipse. On the left-hand side, you can see the Project Explorer. That's basically just a view of the folders that are underneath the main code. So very briefly, what you have here is at the top level, there are really 3 areas of interest. First, the subdirectories that have the vehicles. So these contain complete sets of code for each vehicle, the APM Rover 2, ArduBoat, ArduCopter, ArduPlane, and the old ArduRover. Of those, at the moment I know that ArduPlane, ArduCopter, and APM Rover 2 compile correctly. All right, let me turn my volume up. I'm seeing that some people can't hear me quite well. All right. So, beyond the vehicle code, you can see 2 other subdirectories that are of interest, libraries and tools. Libraries contains all of the libraries that are used by all of the vehicles. So this is essentially the common code that goes across vehicles. And in the last several months, the team has been working gradually to move certain bits of the code into libraries so they can be reused more effectively between vehicles. The other area is tools, and under here there are various parts of the code that are useful for development, including the mission planner, which is ArduPilot Mega Planner, the firmware for the PPM encoder, and the auto test scripts that test the entire code by flight testing it in simulation. So first of all, let's start at the top with one of the vehicles, and I'm going to dive into ArduPlane. And previously I mentioned that you can define your own configurations, and the way you do that is by overriding the defaults and entering new entries into apmconfig.h. So this file here allows you to customize the behavior of the code when it compiles. You would make these changes before compiling, and then when you compile the code, based on the definitions in here, it will enable or disable certain sections. So for example, one of those is to disable hardware in the loop mode. And you can see that's disabled here with this hash define. Now, if you're wondering what parameters can be overridden, you can look at those in the config.h file, which is in each vehicle. And here you'll see all of the various parameters that you can define and change. So let's say I wanted to make sure that my pitot tube was always disabled. And I want to override that. Well, all I need to do then is open APM config, go here, type in hash define pitot mode disabled, and now next time I compile the code, that's going to disable pitot mode. So I basically look into config.h, I see something, and for example here the pitot is on channel 7, and I want to change that. I can go and define that and change it to channel 8 or channel whatever. Now, a lot of these, as Tridge mentions, are actually reflected as runtime parameters. So when you're looking in your ground control system and you look at the parameters page in configuration, you have this long list of parameters. Many of these can be defined at runtime. But if you want to define, some of these can be defined at runtime, and if you want to just hardwire them in the code, APM config.h is the file you would change. All right, so for the next part, I'd like to invite one of the ArduPlane developers to perhaps go for a quick guided tour through the ArduPlane code base. Any of the ArduPlane developers on here who would like to try that?
I'd be happy to do that if you like, Andreas.
That would be super. Okay. None better. So Tridge, a 5 or 10 minute overview of the main ArduPlane code would be fantastic. Thank you. I will follow along as you're talking, or I can give you control.
Okay. Well, you can control at the moment, I think. Thanks, Andreas. So Arduino sketches. I mean, the ArduPlane and ArduCopter are all based on the original Arduino development model. And that model starts off by having two functions that are required for every sketch. There's a setup function, which is called once when the board boots. Then there is a loop function that's called continuously. So if Andreas can go to line 641, then you'll find at line 641 there is the setup function. And, okay, there it is. There's the setup function. Great. So the setup function in ArduPlane is very simple. It's similarly simple in ArduCopter. And it just calls two functions. One is the memCheckerInit. That sets up a little memory checker that we use. We had some problems in the past with running out of memory on the APM. The APM board only has 8 kilobytes of RAM, and it's very easy to run out of that amount of memory. And so we had some issues. We were getting down to our last few bytes, and so we added a new system called memcheck that provides runtime checking of the amount of memory we have left. If you're interested in looking at it, it's based on a little canary system where it basically sets up some known bytes at particular locations in memory and then periodically checks those bytes to see if they've been overwritten. And that way it's able to check, for example, for stack usage or interrupt usage or any other form of memory usage. So that's what memCheckerInit does. It sets up those bytes, those canary bytes in memory, and then there's a regular check later that checks how many bytes have been used, and that's reported to the ground station via the meminfo message, which then tells the ground station exactly how much memory has been used. So after that, the only other thing in our setup function is init ArduPilot, which is an innocuous looking little function that looks as though it doesn't do much at all. In fact, it initializes all of our hardware. And if we have a look at system.pde, then you'll find the init ArduPilot in there. And init ArduPilot starts about line 59. If you want to jump to, there it is, you've got it. So this is what sets up all of the APM or APM2 hardware. And so if you're interested in exactly how we configure the hardware, how we calibrate it, etc., then init ArduPilot is where you'd start. So you see at the beginning of that, for example, the serial.begin, that sets up the various serial ports. We have 4 serial ports, or 4 UARTs is more accurate, on the APM, and we use all 4 of them. The first one is used for the console, which is either the USB port, or on an APM2 it can be mapped to the radio telemetry port. Then we use one for the GPS, and we use one for a second telemetry port, and then one is used on the APM2 in SPI mode to talk on the SPI bus. So there are 4 UARTs. We set those up. We also set up things like the data flash, which is the little bit of 2 megabytes of flash memory on the APM1, 4 megabytes of flash memory on the APM2. We configure the analog to digital converters. That's what that adc.init does. The APM1 has a special SPI bus enabled analog to digital converter that has 8 channels, and we use those channels for reading the gyroscopes and the accelerometers, and also one channel is used for a temperature, and one channel is used for the airspeed. On the APM2, things are different. It doesn't have that ADC chip, and so that's why there's an if-def, as Andreas explained earlier. Those if-defs come out of config.h, and when you enable APM2 hardware, one of the biggest changes is that we don't use that ADC chip because it doesn't exist on the APM2. And instead, we have a different way of reading on the SPI bus to get the digital readouts from the MPU 6000 gyroscope, accelerometer, etc. So after we've initialized the ADC,
Sorry, just a quick point here. As you can see on Eclipse, one of the useful functions that it offers is that when something is not defined, it grays out that piece of code. So the reason this is gray is because this type of compass initialization is not used in my particular configuration. So that way you can see how the hash define enables or disables bits of code visually.
Yep. So also inside this initialization, we initialize, as Andreas says, the compass, if you've got a compass, and the GPS we can see there, and quite an interesting one. If you have a look at that GPS init line, that's something we've changed quite recently. So GPS init there, where we do and we set a parameter to say how to configure the GPS. This is only for a U-blocks. If you have one of the new 3DR U-blocks and you're using ArduPlane, then it will automatically configure the GPS for airborne 4G mode, pulling 4G turns, up to 4G turns. That changes the filter inside the GPS for how to optimize the GPS output for the type of movements you expect. And we pass in different numbers on ArduCopter and on APM rover, because we expect, for example, a rover is unlikely to be pulling a 4G aerial turn, and a copter tends to pull less sharp turns, and so it can filter more accurately by setting up different parameters inside the GPS. We set up the various the radio controlled channels. So we set up the PWM inputs and outputs, set up the LEDs, so you get those fancy LEDs. We have to set them as outputs so that you can then turn them on and off later. The timer scheduler is perhaps one of the least well understood but most important aspects. The new current code in ArduPlane and ArduCopter use a 1 kilohertz timer for many things. So we use one of the built-in hardware timers to generate a 1 kilohertz interrupt, and that 1 kilohertz interrupt provides a heartbeat or a regular calling of several functions inside the code. For example, it provides the heartbeat behind the APM2 barometer. It also provides the heartbeat behind things like the analog to digital converter, reading the gyros, reading the accelerometers, reading the MPU 6000, etc. So that's an absolutely central part of the way we run the APM2 at the moment. So basically, things happen at most at 1 kilohertz, and so we read data from hardware, basically never more than 1 kilohertz, but often quite a lot less than 1 kilohertz. Then you can see the code that allows for the possibility of entering the command line interface, where you hit enter 3 times to enter the interactive setup. That's a new feature we needed to add for the APM2 because the APM2 doesn't have the little slider switch that the APM1 had for allowing you to choose whether you're in flight mode or not. We needed an alternative way of saying whether you were going into the command line interface or into flight mode, and we decided the simplest was to hit enter 3 times, and so that's where it enables the little hit enter 3 times message, and then it watches for that inside the serial code in the Mavlink module. Finally, we check for the possibility of air start. ArduPlane, unlike ArduCopter, can support the possibility of the board rebooting in flight. We're hoping that that will be an extremely rare occurrence. Basically, it'd be something like a brownout, and in theory, it'll be able to recover and get its leveling parameters, barometer, base pressure, the ground pressure, etc., ground temperature, out of EEPROM, and continue flying. I'm not sure how many people have actually tested that by deliberately rebooting an ArduPlane in flight, but the code is there and to support it, at least in theory. So then down below that, we do the ground start. The ground start does the calibration. So we see the startup ground call there at the bottom of the screen on Andreas's screen. You see the startup ground, and startup ground is the rest of the code that gets called when we know we're on the ground. We're not doing an air start, and it calibrates all of the sensors, and that's what blinks the LEDs while it's getting the level, the 0 point on the gyroscopes for 0 rotation. It also gets things like the 0 point on the airspeed indicator, the expected value when you're not moving, which is why it's quite important if you've got an airspeed indicator that when you're starting up ArduPlane that you put your hand to loosely cover the pitot tube so that you're not getting wind if it's a windy day, flying past your pitot tube and giving it a bad offset. The barometer, it zeroes the barometer by measuring the temperature and the pressure at startup, so that it knows what the base pressure is, so that when you get a lower pressure it knows you've gone up in altitude. And it also tries to connect up to the GPS. So that's basically it. Oh, and trimming the radio, getting the 0 settings for the trim from your transmitter, which again makes it important that your transmitter is turned on when you boot ArduPlane, because otherwise it'll get the wrong trim values, which would mean that it wouldn't fly very well once you take off. And finally, it says that it's ready to fly, and the main flight code takes over, and all of your hardware is initialized. So that's it on the main startup of ArduPlane. I'm not sure, did you want to go through anything else, Andreas, or do you want to, is that my 5 minutes up?
I would like to very briefly, if we could, talk about the 4 loops that are in here and then compare them to the timer loops that are in ArduCopter, because I think that's an important part of the non-real-time operating system.
That's right, that's right. We're primarily either polling or interrupt driven in ArduPlane and ArduCopter. We don't have a real-time operating system, which means there's only ever one task happening at a time. Now, in order to cope with multitasking, what we use is interrupts. So that means that the code regularly gets interrupted to do something else. For example, that 1 kilohertz interrupt that reads the gyroscope and the accelerometers on the APM1, and approximately 100 hertz interrupt that reads the barometer on the APM2, and various other interrupts like that. Then there is the main loop, which the Arduino environment sets up to be called continuously. We then ask, the first thing we do is check how long it's been since we were last called. and that's for that millis minus fast loop timer. Millis returns a 32-bit number, which is the number of milliseconds since the board was booted. And we're checking whether that's greater than 19. If it's greater than 19, that means it's at least 20, which means that we've gone more than 20 milliseconds, or at least 20 milliseconds since we were last called, which means we want to do the things that we are interested in doing at 50 hertz. And the fast loop on ArduPlane is a 50 hertz loop, so we call the fast loop function, and it does everything that we want to do at 50 hertz, which is primarily the stabilization and the output values to the servo. You can then see that after we call the fast loop, we call medium loop. Now you might think, okay, that means that medium loop is being called at 50 hertz. But the trick that's used inside medium loop is it uses a little switch statement to divide medium loop up into 5 stages. So the first time you call medium loop, it's got this little medium loop counter. The first time you call it, the counter is 0, and it does the case 0 case. And when that is 0, then what it does is a 10 hertz calls. So all of the stuff within that case 0 is called at 10 hertz. Then all the stuff with case 1 is also called at 10 hertz. So this gives us a breakdown from 50 hertz down to 10 hertz operations. So you can see, for example, that the main navigation code updating the direction that we're trying to fly the plane is called at 10 hertz, whereas the stabilization, the setting of the servos, is called at 50 hertz. We can also see things like the altitude read from the sonar, if you've got a sonar, and also from the barometer, that's called at 10 hertz. Now that can be a little misleading, however. I'll just tell you something about that because that's been updated recently. And you see that update out function, which you can see is called at 10 hertz. So you might think that means we're reading the barometer at 10 hertz. Now on the APM1, that is actually true. We are reading the barometer at 10 hertz. And the reason for that is we don't currently have an interrupt-driven I2C library, which means we have to poll I2C devices, and the APM1 barometer is an I2C device, which means we have to call from the main loop when we want to read the barometer. On the APM2, however, it's an SPI device, and we can currently support interrupt-driven drivers on the ArduPlane code and ArduCopter. On the SPI bus, and so the barometer on the APM2 is called at 1 kilohertz. It then downsamples that to 100 hertz, and it internally averages between the times when you call update out. So update out does a barometer read, but in between times there will have been 8 samples of pressure and 2 samples of temperature. It does a 4-to-1 split between pressure and temperature in its interrupt read routine, which means we are actually reading and averaging the pressure at 80 hertz rather than 10 hertz, which means we now get quite an accurate and smooth measure of the pressure. One of the issues with autopilots is that the barometer readings can be quite noisy, particularly on helicopters, on multicopters, because of the wind from the blades of the propellers can cause a lot of turbulence around the barometer, and that causes the barometer readings to be quite noisy. The change that we made just a couple of weeks ago to read that at 80 hertz using an interrupt-driven driver means we now get a much smoother altitude reading, which is particularly important for things like calculating climb rates, which is important for altitude hold on a copter. And it also helps on the DCM solution calculating the expected vertical acceleration in our discrete cosine matrix attitude solution code. And so it's a little bit misleading there where you see update out called at 10 hertz because you might think our barometer is just 10 hertz when in fact it's running at a 80 hertz pressure rate. Okay, then update commands there also at 10 hertz. That update commands call just above the screen there, a few lines further up. That is the call to check for the next command in our mission. So if you've loaded a mission for automatic flight where you've got a set of waypoints, then what it does is at 10 hertz it goes and checks whether you have completed the previous waypoint, ready to move on to the next one, which means it won't update the waypoint stuff at better than 10 hertz. Then the next one, we have the navigation tuning check, and another one. This doesn't do very much apart from write a bit to the log file. So at 10 hertz, we write out some log information to the data flash, and finally we read the battery at 10 hertz down the bottom there. Now, in fact, that doesn't do very much at all. Reading the battery is now an extremely fast operation. It used to be quite expensive because reading the battery used to require read of an analog-digital converter and polling the ADC. That's now interrupt-driven, which means it now only takes a few microseconds to read the battery, and it averages it over the past few hundred samples, which means this could be moved into the fast loop if we wanted to. Then it calls the slow loop. And the slow loop uses the same little switch statement trick to scale down 10 hertz down to 3 1/3 hertz. Does that by dividing it by 3, case 0, 1, and 2. And that gives us a 3 1/3 hertz calls. And we do things like read the control switch from the radio. That means that when you flick modes, it won't change modes in the plane at better than 3 1/3 hertz. So you'll get approximately 1/3 of a second delay when you switch modes before it actually takes effect. Now that can actually be quite a bit of movement. If your plane is traveling at 30 or 40 meters a second, it could mean you've moved another 10 meters. But human reaction times aren't that fast, so it usually doesn't matter all that much. It also checks the little thing down the bottom there. It's quite interesting, the check USB mux. That's what supports automatically switching between the USB connected telemetry versus the radio connected telemetry on the APM2. There's a little hardware mux that switches the serial port, the UART, between the USB connector and the telemetry connector, and it's going and checking a pin set by the 32U coprocessor. And when that pin goes high, it knows that it needs to switch across to the baud rate that you've defined for the radio telemetry link, because it's quite common that people run the USB link at 115 kilobaud, but it's more common to run the radio links at 57 kilobaud. So it needs to check whether you've switched between the two and change the baud rate appropriately. And finally, you see a 1 second loop down the bottom there. That's called once a second, and it sends a little heartbeat just to tell the ground station that everything's okay, that the main loop is running. And that's really about it as far as the main timing loops, which Andreas asked me to explain. So any questions about that?
Yeah, this is probably a good point to pause and see if we have questions on the loop timers or on ArduPlane, and then we're going to take a quick look at some of the other areas like navigation and then move to ArduCopter.
No questions? Good, it's all clear. That's excellent.
All right, superb. Moving on. Thank you so much, Rich.
No worries. So what do you want to look at next, Andreas?
Well, the next area that I think people would be interested in is the navigation.
Okay.
And Navigate PD. Just explain how the plane navigates, really.
Okay, so navigation in ArduPlane is based on waypoints. As I mentioned earlier, you can upload a set of waypoints to the APM, which is then stored in the EEPROM, and those waypoints contain a latitude and longitude and an altitude, usually as a relative altitude relative to the, using the barometer relative to your ground altitude when you initially turn the APM on. And what the navigation code is designed to do, its input is your GPS location and your orientation, your attitude, the roll and pitch and yaw, so you know what heading you're on. And its output is the nav roll and the nav pitch. They're the two primary outputs. So the nav roll is the roll in centidegrees, hundredths of a degree, which is what roll the plane should try and achieve for the next tenth of a second. So this is called every tenth of a second, and it wants to know how much bank angle it should hold the plane at for the next tenth of a second. And it does this by finding the bearing between our current location, which is based on our last GPS fix, and the next waypoint that it's currently trying to fly towards, and it gets a target bearing. So the target bearing is how many degrees it is between where we are at the moment, the degrees on the compass between where we are at the moment and where we're trying to go. And then we need to know what our navigation bearing is, which is basically what direction we want the plane to point in. And so we just set our navigation bearing equal to our target bearing, which is very simple. And so we basically want to fly directly towards that waypoint. Now, there is some code elsewhere in this file that does some slight correction on that navigation bearing based on cross-track, where it adjusts the navigation bearing to be not quite directly at the next waypoint, but instead trying to move us back onto the line joining the previous waypoint at the next waypoint. And that's called cross-track correction. And there's a lovely little demonstration, the flash demonstration in the ArduPlane wiki that was done by Jason Short that demonstrates how cross-track correction is done. So anyway, we work out what the target bearing is, and then we call update navigation, which then updates the nav roll and the nav pitch. So update navigation, the main output is what roll we want to achieve, and then it's up to the stabilization controller during the main loop, the 50 Hertz stabilization controller, to get the plane to have that particular amount of roll and the correct amount of pitch. So really this navigation is fairly simple. There's a few little bits regarding loiter. You can see, for example, loiter delta. That's coping with, in fact, in the current code, it's no longer as critical as it used to be. It's trying to check whether we have gone right around a waypoint and missed it completely. We've got some new code that went in a couple of weeks ago that is based on crossing a finish line, of crossing a plane that is perpendicular to the path between the previous and next waypoint. And in fact, this loiter delta is no longer critical. It's still in there, but it's very unlikely to be triggered in any normal sort of flight conditions. So then if you go to update navigation, and the update navigation code is in, let me just find that code for you, that's in ArduPlane.pde. It jumps back, and all that's doing is that then, if we're in auto, it calls verify commands. So it's a little bit convoluted here. And verify commands then goes into command process, and it basically wants to check whether we have completed a waypoint, completed the next command, which may or may not be a waypoint. There's lots of different types of mission items that are supported in ArduPlane. The most common is a waypoint, but there can be things like, for example, takeoff and landing and other things like that. Takeoff and landing is perhaps a little more advanced than we want to go through in this initial tutorial. So the navigation is relatively simple. It basically works out the bearing for the next waypoint, calculates what roll we want to achieve in order to move towards pointing at that bearing, and then it's up to the stabilization function to try to achieve that roll. And similarly with the pitch, it works out what our altitude is relative to our target altitude for the waypoint, and then it calculates what pitch we want to be at in order to try to move towards that altitude. And so it gets a little bit more complex when you've got an airspeed sensor, because it does more fine-grained control based on the throttle and an energy calculation based on your total kinetic and potential energy of the aircraft. But for the non-airspeed sensor case, it's relatively simple. Basically, if it wants to go up, it raises the pitch, and if it wants to go down, it lowers the pitch. And so it tries to track your altitude based on what it calls the altitude error. And the altitude error is just the amount of difference in centimeters between the altitude that you're trying to achieve and the altitude you're currently at, and it tries to get that altitude error down as small as possible. Okay, is that enough on navigation, Andreas?
Yes, it is. Thank you so much, Serge. Much
No worries.
appreciated. All right. So again, we're going to pause just a few seconds here to see if there are any pressing questions. And if not, have a look at ArduCopter.
Could we have some explanation about the auto launch and auto land?
Sure, absolutely. I'm going to ask Tridge to help me with that and the auto
Sure,
launch
very happy
and auto
to.
land.
Okay, so auto launch and auto land, first of all, you need to understand the limitations of the current code. Both auto launch and auto land are designed for, in the case of launch, for hand launch or catapult launched planes. It's not currently designed for wheeled planes which need to steer on the runway. And so if you've got a plane that tends to keep along the same line and tends not to veer to one side when it's launching, doing a rolling takeoff, then it can work, but it's really fairly hit and miss. And one of the things that we'd like to do is add support for wheeled takeoffs. Similarly with landing, landing assumes that you're doing a belly landing, and it doesn't attempt to then steer using a nose wheel or tail wheel once you've touched the runway. Okay, so the way auto launch works is, first of all, you need to have a launch or takeoff command in your mission. And so if you have a takeoff command in the mission and then you enter auto, then the plane will fire up the engine and it will try to, or it'll just increase the throttle, and it will try to keep the heading pointing along the current compass heading. Now, you must, in order to do auto launch, you really do need a compass rather than a GPS. And the reason for that is that the heading for a GPS is notoriously unreliable at very low velocities. And when you're initially taking off, you will have an extremely low speed, which means your GPS heading is likely to be complete rubbish. It might be pointing in the exact opposite direction the plane is pointing. And so the way it works is when you enter a takeoff command, it will raise the throttle and try to use either the rudder or the ailerons to steer the plane along the current course until it reaches a minimum takeoff altitude that is specified in the mission command. Once it's reached that takeoff altitude, then it considers that the takeoff has been completed and it moves on to the next item in the mission. And so this works particularly well with, say, catapult launches or hand-launched planes. For landing, again, you have a land operation in the mission, and that land specifies the target location where you want to touch down. So the plane tries to glide in along a smooth glide path to touch down. It's highly recommended that if you are going to do automatic landing that you have an airspeed sensor. And the reason for that is landings are typically performed fairly close to the stall speed. You generally don't land at high speed. So if you're fairly close to the stall speed, it's quite critical that you not go below the stall speed, otherwise your aircraft will stall and will just fall out of the sky. So in order to keep yourself just above the stall speed, you first of all need in your mission a mission command that sets your target airspeed. So you'll find in the set of mission commands there is a special sort of mission command that sets the target airspeed, and you typically want to set it to a little bit above your stall speed, say your stall speed plus 30 or 40%. The ArduPlane will then try to keep your airspeed at that target speed, and it will try to lower your altitude slowly towards the landing point. Once it gets within either 3 meters of the vertical altitude of the landing point or 2 seconds predicted position of the landing point, it will cut the throttle to 0. And that's for planes that have a propeller that you don't want to hit the ground. You want to make sure the propeller is completely off when you're landing. It is a little bit of a problematic. We have no throttle cut capability for petrol or nitro engines. So you have to rely on the fact that it will set a very low throttle, and then you may want a separate throttle cut on your transmitter, or you may want a servo set operation in your mission that sets a particular servo to cut the throttle completely to disable the ignition on a nitro or petrol plane. So it then cuts the throttle and tries to glide in, and once it reaches that magic point of 3 meters vertically or 2 seconds in horizontally before the landing point, it will also lock its heading. So what it will do is it will take the current compass bearing and it will try to hold that compass bearing. So it doesn't try to turn. And the reason that's important is if it tried to turn, that would roll the plane over and your wing might touch the runway and your plane might then flip over as the wing catches. So it tries to hold the plane as level as possible. There's certainly a lot of scope for improvement to the automatic takeoff and landing code in ArduPlane. It is workable at the moment, but the obvious missing feature is wheeled takeoffs and landings where it needs nose wheel or tail wheel steering, and that's something that I'm planning to work on in the next little while. So is that enough an explanation on takeoff and landing?
That was excellent. Thank you very much.
No worries.
One last question that is related to that. Does the ArduPilot use sonar, or is it just for ArduCopter?
There is sonar code in ArduPlane, but it's untested. I've never flown with a sonar on my plane. I have flown it on my copter. Doug has experimentally tried automatic landings using sonar on ArduPlane, but while the code is there, it's disabled by default, and it hasn't had enough testing for us to call it mainstream. We would need somebody to do, the ArduPlane is a community project, and we rely on members of the community such as yourself to do testing and provide feedback and to basically take ownership of particular features that you're interested in. So if you've got a particular interest in sonar-based altitude control in ArduPlane, then I'd encourage you to experiment with it and to get involved and to submit any patches that may need to be updated. Either that, or you'll have to wait for one of the other existing developers to get interested in that feature. The only person that I know of that has had interest is Doug, who's of course was written much of the ArduPlane code. He did a blog posting a couple of months ago about his experiments with sonar for automatic landing in ArduPlane. Those experiments were not particularly successful. Basically, he found at the sorts of speeds he was at, particularly when coming in over grass, that the sonar was not accurate enough to provide good landing information. And so he didn't consider it to be particularly successful, the test that he'd done. It may be that with the recent DCM updates that haven't actually been released yet, but are in the current Git master tree, that they have improved our pitch estimation code considerably, and it may be that that combined with the better smoothing that we now have on the sonar analog to digital converter, we now have much more accurate smoothing available because of the interrupt-driven A to Z code. It may be that the sonar is now worth a look again on ArduPlane, but Doug hasn't had time to rerun his experiments. If you're interested in doing some experiments with sonar for auto landing in ArduPlane, then please get in touch with me, and I can perhaps give you some guidance on what needs to be done. Or just experiment with it and look at the code yourself and see how well it works. I'd be very interested to hear whether the recent DCM updates combined with the much faster reading of the sonar that we now support has been sufficient to make sonar-based landings more of a practical reality than it was previously.
How do we go about getting, contacting you?
You could friend me. I'm Andrew Tridgell on the forums, and you can become a friend and send a message to me there, or you can send me an email at andrew@tridgell.net. I'll just type it into the little chat thing here. Don't be too discouraged if I don't answer immediately. I do get rather a lot of email, so I don't keep up with all of it. So you try again. You could also contact me at Skype. I'm Andrew Tridgel, on Skype. A lot of the ArduPlane developers use Skype for chatting and for screen sharing. You're very welcome to grab me on Skype and we can share a screen and discuss the Sonar code. That's particularly useful because you can then share your desktop with mine, and I can give you a personal little code tutorial, a bit like Andreas is doing for the whole group now. Or I can share my screen with you and show you what I'm working on and what the suggested code changes might be to make Sonar more of a reality. But the first thing is just to look for the existing Sonar code in ArduPlane, to enable it and to understand how it works, and to test it, to make sure that when you have an APM board with a Sonar attached, that when you raise it above your desk, that it accurately measures your altitude in your ground station. It should get your altitude to within a few centimeters. One of the areas that I don't think is particularly well developed is the automatic transition between Sonar altitude and the barometric altitude. Plus, I don't think we've got particularly good code for calibrating your Sonar. It's quite important to know the calibration between the reading that you get in the Sonar and the actual altitude, and we need some better mechanisms for calibrating that to ensure that we have an accurate altitude in centimeters. Or you can, the standard calibration should work with the most common sonars, but I really would like to have a better calibration system than we have now.
Excellent. The reason that I wanted, I have redesigned actually APM 2.0 with a lot of addition, and I wanted to get a hold of whomever that I need to talk to on that. I'm a chief technical officer of telecommunication companies, and I just got interested in this. Okay, so.
Right. So you built your own board. Have you built your own APM equivalent board? What CPU?
The same CPU, but I have put a whole bunch of protection. I kept on reading on all the blogs that people having their unit malfunctioning and sending it back to 3DR. If you look at the APM
can we take this discussion offline for the Q&A?
Yeah, if you maybe
continue the tour with ArduCopter, and then please take the discussion to the chat window so we can continue. So,
yeah, go to the chat window and maybe then grab me on Skype later and we'll have a personal discussion, and I'd be very interested to hear about your board.
Excellent. What was your Skype name?
Andrew Tridgel, with a capital I and a capital T. I'll just type it in again in the chat window. So if you have a look now in the chat window, you see my name there.
Okay, thank you.
You're welcome.
Thanks, Andrew.
Thank you very much.
Okay, thanks, Andreas. Over to you.
Thank you. All right, so I'm going to dive in and look at ArduCopter. And ArduCopter, really what you'll see is two things. You'll see that a lot of the code is very similar to ArduPlane. So in terms of the overall design approach, very similar. However, of course, there are some critical differences. And the most important difference is actually the difference in the speed of stabilization. Obviously, a plane is inherently aerodynamically stable. If you stop doing stuff, it generally just continues to fly. With a copter, if you stop doing stuff, you are 5 milliseconds from falling out of the sky. So that's why you'll see that some things work slightly differently. Of course, the loops are running at higher speeds, and here we have a much faster main loop. And I believe that's currently called at 100 hertz. Let me just get down there. All right, so this is the main loop in ArduCopter. As you can see, the two special functions, setup and loop, that are part of the Arduino code are here too. Again, very similar structure with the memcheck and the initialization function. Just like in ArduPlane, init ArduPilot will go and initialize all of the hardware, and that can be found in system.pd. So as you can see, the structure of the code is very, very similar. All right, if you are not currently speaking, if you wouldn't mind, please muting your microphone. Thank you, just to avoid echo. All right, once again, as you can see, the timers use use interrupt, so this loop is called basically as frequently as possible. One of the differences you see in ArduCopter versus ArduPlane is that rather than using milliseconds, the timers are actually based on microseconds because we want to be able to have some fine-grained control. Here, the 50 hertz timer is actually a slow timer compared to the super fast loop, which we want to run at 100 hertz or more. So the fast loop in the copter is running faster, and that's so it can do this very important function here. And what set servos for is basically setting the motor outputs. Now, I don't know if Randy is online, but if he is, I would like some help in touring this particular area of the code. Again, oh, there he is. Yes, so Randy, if you want to jump in anywhere here, I'm sure you know more about copter than I will ever learn. So I'll continue in the meantime. As you can see, the loop strategy is very, very similar to ArduPlane. So for example, when we're calling medium loop in at 50 hertz, we then split it into 5 10 hertz sections to run 5 different sets of capabilities at 10 hertz. And many of the other parts of the code are very, very similar to the way that ArduPlane works. All right, now I think probably the next part to look at is how you get information from the input to the motors and through the PID loops. That's an area that obviously is very critical. That's how the ArduPilot works, by sitting between the inputs and the outputs. So maybe Randy can tell us a bit more about that particular flow. Randy? Randy, are you there? We cannot hear you.
Hello? Hello?
Ah, yeah, we can hear you now.
Okay. Okay, sorry,
With
yeah,
a lot of background noise.
The audio. Oh, really? Okay. Let me dial back in again, maybe, as long as I'll dial back in.
Looks like Randy just left.
All right, I've got a question here. Can we please cover software in the loop and what is the purpose of Arduino cpp.exe? Okay, I have no idea what Arduino cpp.exe does, but I can certainly talk about software in the loop. So what
Yeah,
software in the
actually,
loop does, yes?
I posted this question. I asked this question because this executable is in the download section, so I was wondering that probably this is the C++ compiler to compile the APM.
Ah, yes. No, the best approach to compile the APM, you can see all of the prerequisites in the first 6 slides of this presentation, which I'll be sharing. It's a Google Doc, so it's already shared, and I will be posting more information on that after the webinar. But what you need in order to compile is the Arduino IDE version 101, which you can download from the Arduino website. So I don't know what Arduino cpp.exe is, but it's not necessary for development.
I think it's, you mentioned a while back that it is possible to compile a software copy so that you can run it without having a hardware box, which is good for development.
Correct. I do all of my development in software-in-the-loop mode because that way I can simulate the APM. So in order to do the software-in-the-loop, it's actually quite easy. From the command line, if you change directory to ArduCopter, for example, if instead of typing make APM2 to make the APM2 version, you type make space SITL or SITL, you will be able to compile an executable version. Let's say you're on a Linux machine. If you do that, it will compile a Linux ELF executable. On a Mac, again, it will compile an ELF executable. So you can do that to compile an executable version. Now, when you execute that on your computer, what it does is it starts up a simulated APM board, and it starts running the code. Instead of serial ports, it has TCP ports. So serial port 1, the console, is mapped to TCP port 5760. And it will tell you that when it starts. Serial port 3, which is usually the telemetry, is mapped to TCP port 5763. And so that way you can connect to those ports. So for example, if you telnet into ports 5760, you're going to see what you see on the terminal when you're on Mission Planner. You're going to see ArduCopter version 2.6 initializing, blah, 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 ready to fly. And if you connect to either of those TCP ports with a ground control system, such as Mission Planner or Q ground control or MAV proxy, then that will allow you to control the vehicle just as if it was connected over telemetry. Using a joystick, for example, in Mission Planner, you can push right rudder, arm the motors, and take off. And it will fly around. You can also redirect the output of that into a popular flight simulator, such as Flight Gear, or X-Flight, I guess is the other one. And you can view the copter or plane flying on your screen in a simulated environment.
Thank you.
Hey, can you guys hear me? Hey, Andreas, can you hear me?
Yes, we can hear you perfectly now, Randy. All right.
All right.
Let's do a quick tour now from input to output, going through the code with Randy. Thank you.
Yeah, sorry about the audio problem. I'm not sure what was wrong there. So,
no, not at all. Worth waiting.
Okay, so what I wanted to go through actually was just kind of a top to bottom, code walkthrough of how flicking the switch on your controller, gets all the way down to the motors. So
absolutely great.
So when you've got your controller, right? You obviously you've probably seen the Mission Planner setup screen where you can set what each 6 positions of your switch, or however many positions your switch has, to correspond to actual flight modes like loiter or whatever. So what happens there is on that screen when you say set position 1 to be stabilized, is the Mission Planner writes a special number into a parameter. So if we go to parameters.h, line 259. So there you are there. So those are the 6 positions where the Mission Planner is storing the the actual flight mode that you've requested for that position. So a little number will go in there from about 1 to 10 or so. What those numbers mean is actually in the defines.h file at line 114. So there you go. So when you select, for example, loiter, number 5 would be written into that first parameter. So then what happens is If you go into ArduCopter around line 380 or so, you'll see that there is a control mode variable, and that is where the current flight mode is held. So the way that all through the code, you'll find that it looks at the control mode, and so that controls what the current control mode is. The way that control mode gets updated is in ArduCopter PDE line 1329. You'll see that it's calling this read control switch. Actually, I think Tridge showed you this earlier. So this is being read, in the slow loop, right, at 3.5 hertz, and that function's purpose in life is to look at the current switch position and update the control mode variable. You can actually see where that read control switch function is implemented in control modes.pde right at the top. Andres, can you go to control modes.pde? Yeah, right at the top. So right there. That's where it's implemented. You can see it right at the top there. It has the read switch call. And if you look into that, you'll see that it has a hard-coded list of radio values, where it's decoding basically what's coming into the radio, and then deciding which what control mode it should switch into. So then the next important thing, yes, is this set mode call. So what that's doing is that's taking the parameter, putting it together with the switch position, and then changing the actual flight mode that the copter's flying in. So set mode, you'll find, is in system.pde, line 415. So you can see it's got one parameter there, which is the mode, so that would be something like, for example, stabilize. And if you go down a little bit more, you will see, just keep on going down. Yeah, so it's just at the control mode right there to the mode that you've passed in. And then right here, this is the important bit, this big switch statement here. So this is where it is taking the flight mode, like stabilize or loiter or whatever, and setting 3 other critical variables. So a flight mode like stabilize is actually made up of 3 kind of sub-modes. It's a yaw mode, a roll pitch mode, and a throttle mode. So that's a really, I guess, really critical, critical thing to understand. And so any one of these flight modes, you'll find that it's made up of a combination of different yaw, roll, pitch, and throttle modes. So, for example, you can see here that let's have a look at loiter. Loiter has a yaw mode, which is loiter yaw, a roll pitch mode, which is loiter RP, and a throttle mode, which is loiter throttle. But if you actually then went, those are actually just hash defines. You'd actually find, if you look through the code a little bit more, that loiter yaw is actually just yaw hold. So that's a you'll find that in defines.h at around line 16, I think. Yeah, just go into defines.h. There you go there. So these are the actual possible modes for each of the 3 access controllers. That's what I call them. I call them access controllers. But the yaw mode can have one of these 5 possible values. So moving along, how do these once we have these 3 variables set, the yaw mode, roll pitch mode, throttle mode set, how does that actually make a difference to the controllers that are being executed? So if you go back into ArduCopter around line 1075, you'll find that in the fast loop, which is running at about 100 hertz, we call these 2 functions. You can go to, yeah, ArduCopter.pd line 1075.
Sorry, 1,000 what?
1075. Yeah, there we go there. So this is where we actually make use of the yaw mode, the roll pitch mode. So let's these functions here are being called at 100 hertz, like I mentioned. The throttle mode is actually called at about 50 hertz, a little bit further down, but never mind that. So, right, if we can now go to update roll pitch mode, which is in ArduCopter PD at 1589. Sorry to jump around. So this is where it actually takes that, actually takes the roll pitch mode and does something with it. So you see the switch statement here. This is really quite key. So for example, you can see right at the top here, it's looking at the roll pitch mode and it's checking, is it acro mode? Is the roll pitch currently the acro mode or not? If it is, then what we want to do, what it needs to do is it needs to first look at the control inputs from the pilot, which are sitting in these GRC control in. It needs to decode those, right? And it needs to then send them into this, get into the PID controllers. But actually, it doesn't go directly into the PID controllers. What it does instead is it calls these functions like get stabilize roll, which are inside of attitude.pde. So, yeah, so just to recap here, what we're doing here inside of the switch statement is we're looking at the roll pitch mode. We're decoding the user's input from their, from their controller, which is being held in the RC1 and 2, which are, the roll and pitch input from the pilot. We're then, we're then passing that into functions which are held inside of the attitude.pd, like get stabilize roll. Then what we will do from that, those functions will return to us an output, like a desired roll output, which we put into servo out. And then later on, you'll see that we'll pass those server outs into the motor's code. But before we do that, let's just have a look at into the attitude.pde at say get stabilize roll. So there we go. So there's get stabilize roll. So what's being passed in here is, if you remember, the pilot's input. So say the pilot had his stick over, leaned over at 20 degrees. That a number 2,000, which is the number of degrees times 100, would be passed in as the target angle. So then what this code here is doing is it's taking that target angle. It does a couple of checks and balances on it, like making sure that it isn't too large. It's also comparing it. It compares that target angle being passed in with our current angle. That actually gives you the error, right? So say, for example, we're actually at 5 degrees now, but the pilot wants 20 degrees, so you'd come up with 15 degrees. And then you can say, yes, we put some limits on it to make sure that it's not too big. And then we pass it into the PID controller. So this GPI stabilize roll, that is a PID object. And it's already got all of the PID values that you might have set up through the through the mission planner. All the gains, etc., would be held inside of that PI stabilize roll object. So what we do here, right, was we passed in the angle error, which was 15 degrees. That will come back with some kind of angular output, which we put again into, comes back with the rate that it would like. So say, for example, it's a 15 degree error, it'll come back and say, oh, okay, I want to therefore, roll over at, 35 degrees per second, something like that. That would come back from that PID controller into the target angle. We then take that and we, you'll see right at the bottom of the function, we actually pass that into the get rate roll right there. You can see right there, you see that get rate roll. So that's where we're actually taking the output from the stabilized angular controller and passing it into another controller, which is a get rate roll. I don't think we need to go into that, but the get rate roll is going to be another PID controller, which is going to take that desired rate and then pass back it's going to pass back a number, which we will then in turn pass back up to the main ArduCopter code. So let me, I ran over that a bit quickly. I'm going to go through a little bit more, but I just wanted to just have an opportunity here for anybody to ask questions in case I wasn't perfectly clear on some parts. Okay, so I'll just keep going then. All right, fine. So we've just run through, the get stabilized roll, and the PID controller has been called. It has come back with a basically an output that needs to go to the motors. So can we go back to the main ArduCopter code, ArduCopter.pde, around line 1589, maybe a little bit lower than 1589. Yeah, so just keep going down here. So yeah, okay, let's just go down to the roll pitch stabilized, because that was the controller we were just looking at. So just go up a bit more. Sorry, where are we? It was 1589. Oh, here we go, good. Oh, yeah, here we go, great. Okay, so you can see, right, we have, if you go down just like about 6 lines or so, you see this, GRC1 servo out equals get stabilized roll. So, we were just talking about that function a moment ago. It's come back with basically an output that it thinks should go to the motors. We stick that into this GRC1 servo out variable. So that's the thing that needs to get to the motors now. So, let's go down a little bit further in the code, another 40 lines or so inside of this ArduCopter.pde, and you will see. Actually, sorry, yeah, actually you won't see it here. So okay, the output that should go to the motors has been put into that GRC1 servo out and GRC2 servo out, which corresponds to the that's the output that should be sent to the motors. So it's not called directly from here. You'll find actually that back at around line 1080, we call the set servos 4 line. So that is where we make use of the outputs from those PID functions and send it to the motors. So we should go to the motors.pde at about line 184. There it is there, you see. So set servos 4 is a very small function, and it just calls the motors.output. Now, this is where we get into the AP motors code, which is a library, and the purpose of the library was really to abstract away all the differences in the different frame types. So if you look at this library here, you can see that we have a whole bunch of different implementations of the AP motors class object, one for each frame type. So yeah, the purpose of each one of these frame types here is just to take the the output that we came up from those PID controllers, like the GRC1 or whatever, and turn that into actual outputs to the motors themselves. So if any, let's have just a quick look at the AP motors try.h. Andreas, can you pull that up? AP motors try.h.
Perhaps quad will be better because most of the people use quad.
I could do that. It's a little bit more complicated, the quad one, but yeah, we could look at that one if you like. So yeah, the additional complexity with the AP motors quad and the hexa and the octa is that
they in turn inherit from the AP motors matrix class. So actually, I'd actually prefer to look at the AP motors try because it's much simpler for now, and then you'll see. Andres, can we go back to the AP motors try?
Yeah, I already have. It just hasn't updated on your end yet.
Okay, sorry.
It's got about 2 to 5 seconds lag.
Okay, yeah, here we go. Great. Yeah, it's updated now. So, if anybody wants to implement a new frame type, all you should have to do is just update the, write a new AP motors class, inheriting from AP motors.h and AP motors.cpp. And the most important functions to implement are right at the bottom here. It's called output armed and output disarmed. And you might remember a moment ago when we were looking at the main ArduCopter code, it was calling a motors.output function. In fact, motors.output function is implemented in AP motors.h. All it does is just check to see if the motors are armed or not. If it's armed, it in turn calls AP motors armed. So, and if it's not armed, then it calls AP motors disarmed. So anyway, let's just have a look at the AP motors armed to see what it does. So we can go into AP motors try.cpp.
Yep.
And let's just go down to the motors armed function. Sorry, the output armed function. There you go. There we go. There we go, right there. So now in this function, the GRC1, GRC2 that we talked about before have been, renamed essentially into RC roll and RC pitch. But these are the same objects. The RC roll is just a pointer to those global objects. So what we do here is you can see we we need to first of all make sure the throttle is it's a reasonable number, not too big, not too small. Then what we do is, for the RC roll and pitch, we call this calc PWM function. What this does is it takes the output from those PID controllers, which was in the range of minus 4,500 to 4,500, which essentially means 45 degrees times 100. We take those, we want to turn those into PWM values, which are between 0 and 1,000, I believe. Right? So that's what these that's what these calc PWM functions are doing. Then what we do is we need to take those numbers for each one of the axes, and we need to turn them into an actual output to a that a servo or an ESC would understand. So this is where the mixing happens, which is specific to each frame. So you can see we've got this motor out array here, and it's got for motor 2, we are going to send it the RC throttle, just the basics pilot throttle. Then we're going to add to it a roll out and also a pitch out. So this is where the mixing is happening. You can you can look at the different frames and see how the mixing is done, but basically they're all just different combinations of the roll, pitch, and throttle provided from the PID controllers. A little bit below that, you see we have something called the Tridges stability patch. What we're doing here is we're just making sure that if one motor goes too high, like above its limit, say above 1,000, that we instead limit it to 1,000, but reduce the opposite engine's output instead. So that that way we don't lose control when our throttle goes very high. So yeah, you see that we implemented a stability patch, and you should do this for any new motor types, or sorry, any new frame types that you create. Then we also make sure that the motors don't go too low. i.e. we don't want them to stop spinning completely, so we make sure they don't go below a certain value, which is I think about 130 or so. There's a little bit of cutoff stuff which I won't worry about, but basically it's just cutting off the engines if they need to be cut off. Then right at the bottom here, you'll see this RC output CH. So this is where we're taking the values that we had inside of, which we put inside of those, motor out arrays, those values for each one of the motors, and we're sending them out on, to the actual ESCs or servos. So this RC output channel call is a call to the APM_RC library, and that library's purpose in life is just to take a PDM output, between 0 and 1,000, and turn that into the radio out that an ESC could actually understand. And that is about it. There's a little bit down here about instant PWM, but that's another APM_RC library function which you can have a look at if you want to. We don't really make use of it anymore, so I won't go over it. So that is kind of it. Just as a recap, we saw how we decode the switch, how that goes, how that is translated into control modes for the yaw, roll, pitch, and throttle, how those are fed into the PID loops inside of the attitude.pe, and finally how those are fed down into the motors. So let me break for any questions. Yeah.
Actually, at this point, we're going to close things up and switch into Q&A mode so we can take everybody's questions. But I believe that completes our guided tour. It certainly is about as much time as we have for a guided tour. So to keep the presentation under 2 hours, we're going to stop the tour now and then switch to questions, which will run as long as we have questions, really, and as long as people are here to answer them. So thank you so much, Randy. All right, so I'm going to turn over to the Q&A section now. You may have noticed that we covered the first 12 or so slides, and we did not cover the last half a dozen slides or so. Those are going to be part B, how to create a patch, compile a patch, and run a patch, and submit new code to the developers. I'm going to be scheduling a follow-up webinar for part B, and then depending on the feedback I get from everybody, we can figure out what other webinars we want to do, how we want to modify this one, and whether we want to do it again, and how often, etc. So with that, I'd like to turn it over for questions. Who has a question for the developers?
I have a question related to sonar.
Yes.
So I see that we are using A to D interface of the sonar. I believe it also has a serial interface. So I'm not sure.
So the sonar, I believe, yeah, the sonar uses an A to D controller on APM1 and APM2.
Yeah. Wouldn't it be more accurate if we use the serial interface where we get the exact number of bits as to what the height is?
Okay, I don't know if it would be more accurate or not. Anybody have a comment on that with the sonar? I do know that we only have 3 serial interfaces, and all of them are being used at the moment. Well, 4 serial interfaces, but between the 2 boards, we use all of them. So part of the reason it's probably not on serial is because we're already using them.
Yeah, that's what I thought.
That's right, Andreas. It's also that we can read from the analog to digital converter much more rapidly. And that's because it's a much lower overhead to read from the ADC, so we can read at maybe 100 hertz or so on the ADC using an interrupt driver, whereas the interpretation of the bytes required to read off the serial port would slow down the reading a lot.
Right. Thank you, Tridge.
I have a question about Eclipse.
Yes?
You have a view that you were showing with the Mega. I was wondering how to get that and also how to compile via Eclipse.
All right. So I had a view. I'm not sure what view I was showing. Let me just pull up Eclipse again. You mean this view that we were using?
Yes, in the Project Explorer.
Ah, yes. So very simply, here's what I did to get this working. So within Eclipse, this is the C++ version of Eclipse, and it has to be the C++ version of Eclipse. But basically, I used right here the new project. hang on, Eclipse has chosen a time to slow down for me. And under C++, you can see Makefile project with existing code. And by defining that and then importing the source code directory that ArduPilot is, it will create a project, as you see on the left. So that's how you import the code. I can probably import it twice just so you can see. So I could call this APM2 work in progress. And yeah, you can essentially pull that into the existing code location. You put the project and finish, and that will pull up a second copy of this. So that's how you get it in. Now for building, there's instructions in the first 10 slides of this presentation. You probably missed the beginning of the webinar when we talked about that. If you change 4 settings in Eclipse to define the builders, I'm not sure if they're actually defined on this particular copy. This is not the one I usually use for development. This is just for the presentation. Under properties for yeah, this isn't the C++ project. So under properties, you would change the build command and the build targets. So you change the build target from all to APM2, and you change the build command from make to make with a build route parameter to tell it where to build. And you can find that information in this presentation that we just presented.
Thank you. I found my issue is that I only have Java available.
Yes, you do need the C++ version of Eclipse, and it's a separate download, or you can download it as a software update for your Java Eclipse if you want to just run everything in one Eclipse.
Thank you.
I actually run the Java, C++, and Python Eclipse in one, so for all the languages. More questions? GDB debugging over JTAG. So I will admit to you that I do all of my code development and all of my debugging in software in the loop. By using software in the loop, I can use standard GDB and software. I can watch variables. I can look at the code executing. I can set breakpoints. I can pause it. And of course, I can simulate various situations like different altitudes and different flight behaviors, as well as fly the vehicle with a joystick in a simulator. So personally, I think the only reason you would use JTAG is if you're actually trying to debug the hardware itself, because you can do most of that for the code and software in the loop. But perhaps someone else who has used JTAG can answer? Is there anyone who knows anything about JTAG?
It's only really used for very low-level debugging stuff. So, I mean, I've used JPEG to do a bit of low-level coding on the 3DR radios, for example, but I've never needed to use JTAG to talk to my APM1 or APM2. But I know that some of the people doing, for example, the programming of the little servo controller CPU, the 32U, they use JTAG to talk to it.
Yeah, so basically JTAG is for the hardware that you can't simulate in software, because if you can, you do. And yeah, so viewer 389 is saying he has a JTAG and just wants to use it. That's always an absolutely great way to explore new technologies, not the best way to debug this particular code. So I would use software in the loop. Now, for setting up software in the loop, this is a bit tricky because it depends on the environment you're running it. And what I would like to do is do a follow-up webinar specifically for software in the loop debugging and development, because I think that will be much more useful to go into detail. All right, so people like that idea. Great. Any more questions?
Yeah, I have a question.
Please.
So I was looking at the auto land feature that Judge was describing earlier, and so if you look at the part where if you don't have airspeed enabled, it sets the nav pitch to just like a predefined pitch, which is called landing_pitch in this case. And,
that's right.
Which file and which line are you looking at so we could actually pull it up?
ArduPlane.pde, line 1039.
All right.
So you'll see the nav pitch gets set to landing pitch. But I can't find where landing pitch is actually defined. I see where it's, initialized, but it's not defined in anywhere that I can find.
Okay, I got mute off? Yep. So the definition of it's defined as a int16 at line 480 of ArduPlane.pde, but it's not set anywhere. So let me just see. Yeah, that looks like it's a bug because we define it and we declare it at line 480 there, but we never set it. And I doubt it's set in a library. I'll just check through the libraries just in case a library, does the wrong thing and sets a global variable like that, but I doubt it. Indeed, that's a bug. Now, I think I know why that bug happened. That's probably because that was lost in the conversion from Mavlink 0.9 to Mavlink 1.0. I'm just checking in the history of our code history to see whether there was any code removed that got rid of the setting of that landing pitch. So I'm just doing a quick search through the code history.
Okay.
Yes, there was code. Okay. Yes, there was code in the handle process condition command that set it, but the code was commented out, and so it didn't actually ever set it there. But that was quite a long time ago. That patch. Let me just have a look at when that patch happened. That was in January. Doug commented out that code in January. So we haven't had landing pitch support without airspeed for quite a long time. It's always been recommended that you have an airspeed sensor, but obviously if you don't have one, then not being able to set the landing pitch is a real bug. So now I could fix that. It's only a fairly quick fix, but given this is a development webinar, whoever just pointed out that bug, would you like to do the fix and then submit it and produce a branch and things, or would you rather that I just commit a fix now?
No, that'd be great. I'd love to fix it.
You'd love to fix it? Okay. Well, perhaps it'd be great to have a webinar on sort of how to make a contribution at some stage. There's also been various blog postings on making contributions. But if you prefer that I sort of walk you through it more personally.
Yeah, so...
Yep, sorry, who is this talking? Is it an existing developer?
Oh, this is Jeff Taylor.
Yeah, hi, Jeff. Yep.
Hi.
Okay, so if you'd like to fix it and submit a patch, then ideally you'd submit it as a branch, and then we can accept that branch and rebase on it, or cherry pick the patch. And I think the landing pitch should be set in the command. Basically, there's a Mavlink